So, section 2.5 today, the power rule. Quick reminder what you had to do over the weekend to find the derivative was that four-step process. How fun was that, y'all? Oh, and while I'm thinking about it, I made a new tab in the Blackboard navigation menu called Homework Help. And what I'm going to do there is I'm going to start cataloging all the homework questions I'm getting via email. I'm just going to put the question and my response linked there. Sometimes it's a typed response or handwritten response. Sometimes it's a video. But I had some questions about this four-step process. So you can find that on that Homework Help tab there. And I just heard my little chime, so let me hop back here. Oh, yeah, Marcus says it was frustrating at first. Oh, gosh. Okay, yeah, deep breaths. Well, here's the good news. So that four-step process is tedious, right? I mean, first of all, there's 4 steps. They involve reading function notation. They involve taking the limit of those 2 points as the distance between those 2 points. And remember, h is the distance between the 2 points. We're shrinking that distance down to 0. So those 2 points are getting closer and closer and closer together till they're essentially the same point, so that the slope of that secant line is modeling the slope of the tangent line at exactly 1 point. Like that's what that limit of the difference quotient is doing. And it works every time for any function I give you, no matter how awful it is, it's going to work. But we don't always want to do that. Okay. Luckily, some mathematicians noticed some patterns, and from those patterns, they generated some rules that we're going to get to follow that help us like bypass this 4-step process. So on the test, just heads up, on test 1, I am going to ask you to do the 4-step process one time for one function, and the function will have a quadratic in it, like an x squared. So I will ask you to find the derivative using the 4-step process one time, and that's it. Every other time you can use the rule I'm about to show you. And then for test 2, we're going to learn a whole nother set of rules. But for test 1, we are going to focus on power functions. So this is a power function. So the rule I'm going to show you only works for functions that are set up in this particular format. So let's look at this format. Always ask yourself when you're given a function, what's happening to the input? So I'm inputting an x. Where's the input being sent? It's being sent to the base. So my input goes to the base. So the input goes to the base. And then your exponent is going to be some kind of constant number. It can be positive, negative, 0, decimal, fraction. It can be anything. It's just a constant number. That doesn't change. So the input doesn't affect your exponent. The input is affecting the base. Okay. And if your function is set up this way, you can use what we call the power rule. So what I have on here are 4 functions that you found the derivative of using the 4-step process. So if you go back and look on your notes from section 2.4, so the 4-step process in section 2.4, use the 4-step process to find the derivative of this linear function. That one, did we really need the 4-step process? No, right? We know that if a linear function is of the form mx plus b, we know the derivative is the same as the slope of the line. The slope of the line is constant. So we know that the derivative is that slope. So we did that 4-step process just to tell us what the slope was, which we already knew, right? So we didn't need the 4-step process for that particular linear function, but we did it just to prove it worked, and we saw it's the same thing as the slope. Then we did the 4-step process for some quadratic functions. Those we did need that 4-step process. And we got a new rule, this derivative rule that calculated like what's the slope of the tangent line for any x input I put in to that rule. Okay, so we're going to get these exact same derivatives today without doing the 4-step process. Okay, this is what we're going to use. We're going to use this power rule. And don't freak out, but this is what it looks like. Okay, deep breaths. Here we go. I'm going to explain it. I'm just letting you like embrace the horror for a minute. Okay, so panic over. Let's look at, remember, if you put your input in, that input is going directly to the base, right? Input goes to the base. Okay. Now this is what it's saying the derivative is. It's saying it's an n. Where did that n come from? That constant exponent, right? This exponent, you have a constant exponent. So what this rule says is the pattern is you drop that exponent down to the front, which we did. This is your exponent. Then we're going to rewrite the base. That x was just the base, right? That was your input. So we're going to rewrite the base. And then we're going to put a new exponent on that base. What is the new exponent telling us there? Well, it's the old exponent n minus 1. You're just decreasing that exponent by 1. So when you drop the exponent down to the front, then you decrease the exponent by 1. So decrease original exponent by 1. And then you see this weird thing over here. You're like, as if all this isn't weird enough. Then you see this thing here. What in the world is that? Well, what was x? What was x representing? The base, right? And then if you have that little tick mark, doesn't that just mean derivative? So what this is meaning right here is the derivative of the base. So then you're going to multiply by the derivative of the base. Whatever the base is, you just multiply by the derivative of it. And right now you're probably thinking, God, I'll just do the 4-step process, right? Like, God, I'd rather do the limit. As h goes to 0, the difference quotient. I promise when you get the hang of this, it's going to be way easier. And the chain rule part is this piece right here, where you tack on the derivative of the base. That's what we call the chain rule. And I'm just introducing it on day 1 because I want to plant that seed really early. And we're going to come back and do all 3 of these derivatives with that rule. But before we do that, we have to agree on one thing. But before I talk about that one thing we agree on, let me pause real quick to see if there's any questions, or maybe go to a status right now. I'm kind of scared to ask, but let me see your face. Go to the status, click your little profile pic, and let me see what you're thinking here. Oh, and there is a question, so go ahead, Andrea. Oh, is that an accidental hand raise? No worries. Okay, so I am seeing lots of shocked faces, lots of confused faces. I was expecting that. I'm not surprised. Let's just see this in action, and then you probably know what to ask. Right now you're like, I'm so lost, I don't even know what to ask. Okay, so let's take a look. This is the one thing we must agree on before we continue. If I gave you this function, f of x equals x, that's a linear function, right? So it's a linear function in this format. Remember, linear functions are y equals mx plus b, or f of x equals mx plus b. If I gave you this function, f of x, and I wrote that in my linear format, okay, what's my understood slope? What constant is understood to be in front of the x? We understand to be a understood 1 is there. And what's the y-intercept? What's the b? If nothing's being added, aren't we just adding a 0? Yeah, so without the 4-step process, yes, Arjana, I am recording this. So knock on wood, right now my recording app is working. Okay, so if we did the 4-step process for this, because up until now, that's all we know for the limit of the difference quotient, right? That's all we know. If I did the 4-step process, I can get the slope of this. We know the slope is just going to be 1. So if you have x, the derivative of x is just going to be 1. We all have to agree on that. So another way to write the derivative of x, instead of in function form, we can say the derivative of x. If f of x is just x, so they're interchangeable, then the derivative of that is just going to be 1. We have to agree on that for right now. If you have a plain old x, that's a linear function. A plain old x is a linear function. There's an understood 1 from the x, which is the slope. So the derivative, which is constant, has to be 1. So you have to agree on that before I show you what we're about to do. So show me your status. Do you agree that the derivative of a plain x, the derivative, the rate of change, the slope of x is 1? Do you agree? Okay, Michael, go ahead. Oh, was that an accident? Okay, no worries. No worries. Okay, so here we go. I'm going to show you the power rule for those three functions that you did the difference of the limit quotient on. Okay, so here we go. So let's look at this first one. Just heads up, this original function is linear. It's a degree 1 function. Isn't there an understood 1 exponent there? Linear functions are degree 1. We know this derivative is 3. We would not do the 4-step process. We would not do the power rule I'm about to show you. We know this derivative is 3, but let's do our power rule. Are you ready? What in the world does the power rule say? Okay, this is what it says. I'm going to write f prime of x because I'm finding the derivative. Once I start the 4-step process and take the limit of the difference quotient, I'm taking the derivative, so I use the f prime notation. Once I do the power rule and start that process, I'm taking the derivative, so I need the f prime notation. And this is what the power rule says. It says you take the exponent, you drop it down to the front. So the exponent was an understood 1. I'm going to drop that down to the front. There was already a 3 there. So what do you do when you drop something down and they're side by side? We multiply, right? So we're going to multiply the coefficient by the exponent I dropped down. Okay, then I need to rewrite the base. The base was an x, so I'm going to rewrite the base. My base was an x, I'm going to rewrite it. Then I need to decrease the original exponent by 1. So if my original exponent was a 1, oops, the exponent goes on the base. The original exponent was a 1, I need to decrease it by a 1. I need to decrease it by a 1. And then I have this minus 7 going on there. What in the world am I going to do with that? What in the world am I going to do with that? Well, let's see. Do you see an x anywhere in that term? No, right? So can I say there's an x to the 0 power there? There's 0 factors of x in that term. Yeah, I could. There's 0 factors of x there. There's no x. X to the 0 power is just 1, right? So 7 times 1 is 7. Having an x to the 0 power doesn't change anything there, but I'm going to follow the rule. So let's follow my rule. My rule says you drop the exponent down to the front. So that's a 0. There's already a 7 there. So it's going to end up multiplying by 7, right? Then I'm going to rewrite the base, which was an x. Then I'm going to decrease that exponent by 1. So it was 0. I'm going to decrease it by 1. Oh man, this is just ugly. But let's clean it up and let's see what we get when we clean all this up. Okay, here we go. Let's clean it up. 3 times 1, so 1 times 3. So now when I'm cleaning this up, this is what I'm doing. I'm going to multiply these together. 1 times 3 is just 3. Then my base was an x. And then 1 minus 1 would be an exponent of 0. Okay. Minus, then I come over here, 0 times 7. 0 times 7 is just 0. And I don't care what this is. This can be any number, can be any amount. What happens if you multiply anything by 0? It's 0, right? Multiplying 0 times anything just zeroes it out. It goes to 0. So this whole thing goes to 0. And let's think about that a little bit. If you have a constant number like 7, is a constant number changing? No, it's constant, right? So if a derivative is a rate of change, a slope is a rate of change. If a derivative is a rate of change, and a number is constant and it's not changing, then we would say its derivative is 0 because that constant number doesn't change. It's always 7. There's no variable component. So it makes sense that a constant number would have a derivative of 0 because it doesn't change. Okay, this still doesn't look like what we got earlier, right? Like I'm supposed to get that the derivative is just a 3 and I have this yucky stuff here. So let's clean it up a little bit more. Let's finish cleaning that up. Okay, so well, x to the 0 power, any non-zero base to the 0 power is just 1. So 3 times 1 is just going to be 3. And then if I subtract a 0, that doesn't do anything. So we do all that work and we get that the derivative is 3. Of course, we would not do that in real life, right? We know the slope is 3. We would not do the difference quotient. We would not do this. But I'm just trying to show you that the rule works. Okay, before I even ask if there's any questions, we're going to do one more because I know that was a lot. And I just realized I forgot to do the chain rule on that one. I'll come back to that. Oh my gosh. I have to get my brain that we want to do the chain rule from the beginning. Because if I don't do it now, students are going to forget to do it on test 2. Okay, let's try another one here. I promise it's going to get better. Let's try another one. Okay. I know what my derivative is supposed to be. My derivative, let me even write it down here. My derivative is supposed to end up to be 6x because we did the difference quotient on this one. I'm going to go straight from this function to this derivative by using my power rule. Okay, let's see what we get. Here we go. Let's do it. I'm going to zoom in a little bit here. So what does the power rule say? I'm starting to take the derivative. And the power rule says you take the exponent, which is a degree 2. This is quadratic. It's a degree 2. I drop it down to the front. There's already a 3 there. So what do you do when things are side by side? You multiply them, right? So that's going to end up being a 6 in a minute. But before I do that, I need to rewrite the base. Here's my base. I'm going to rewrite my base. I'm going to decrease the exponent by 1. And then technically, I'm supposed to tack on the derivative of the base. This is why I forgot to do it earlier. What is the derivative of x? What did we agree the derivative of x was? If you had a plain old x, we have to agree that the derivative of it is just 1. So this whole thing is just 1, and if you multiply by 1, it doesn't do anything. But later on test 2, it is going to do something. So I'm trying to plant the seed now, and even my brain has a hard time planting the seed. But let's clean this up a little bit. What do we get here? Okay, well, 2 times 3 is 6. I have my base x to the first power. If my exponent is a 1, we don't have to write it. It's just understood to be there. So see how I got the same derivative without taking the limit of the difference quotient? I don't know. I think it's kind of neat. You're probably overwhelmed right now. How are you feeling on that? Show me a status. How are you feeling about part B only? Okay, mostly happy, some shocked. I expect some shocked. Let's do another one. We're going to do a whole bunch of these today. Let's do some more here. Okay, let me shrink that down. Let's do another one. If I had done the chain rule on the other ones, we're just going to end up multiplying by 1, so it doesn't change anything. So the fact that I skipped it is okay. Okay, here we go. Let's try another one. And what was my derivative supposed to be? Let me come back up here. We know that our derivative is supposed to end up being 4 minus 2x because we already did that one. So let me write it down here. This is what we're supposed to get. Let's see if we get it. Okay, there's 2 pieces here. There's 2 terms, so I'm going to do the power rule on the first term, and then I'm going to do the power rule on the second term. So let's see what we get. Okay, so I'm taking my derivative here. Okay, here we go. So there's an understood exponent of 1 on this first term. I drop it down to the front, but there's already a 4 there. So 1 times 4. Then I rewrite my base, which is an x. I decrease the exponent by 1, which would make it a 0. And then technically, I multiply by the derivative of the base. But right now, we know the derivative of the base is just 1. So let's just clean up that first part, and then we'll do the second one. So all I've done right now is just this first term. I'm going to clean all that up. So let's see what that comes out to be. Okay, 1 times 4 is just 4. X to the 0 power. Well, any non-zero base to the 0 power is just 1 times the derivative of x was just 1. If I do 4 times 1 times 1, don't I just get 4? Yeah, right. So that's just 4. Okay, now let's do the second term. Just shrink this down. I did not give us enough room to write here. You can tell I've never used these notes before. Okay, let's do that second term now. X squared. Okay, let's do that one. Here we go. Okay, so minus, because there's a subtraction separating the terms, so we're going to subtract something. We bring the exponent down, so we bring down the 2. There's technically a 1 in front if you want to write it. Then we rewrite our base, which was an x. Then we decrease the exponent by 1. It was a degree 2, so if I decrease it by 1, it's going to be degree 1. And then technically I tack on the derivative of the base. So let's clean that up. So I have my 2 there. X to the first is just x. And the derivative of x is just 1, so I don't need to write that. If I do 2 times x times 1, 2 times x times 1, isn't that just 2x? So we got that derivative by following this power rule for each piece, for each term, and we didn't have to do the limit of the difference quotient. I don't know. How are y'all feeling on that? Give me another status update after this last one. Are you feeling any better? Okay. Well, if you want to, you can take the limit of the difference quotient on every single problem. It's just going to take forever. And plus, then I have to grade it. And you want to keep your grader happy, right? Okay, we're going to practice some more. Don't worry. We're going to practice some more. Deep breaths. Okay, here we go. And that's super messy, but I'll write it up pretty for the answer key. Okay, so these are the rules that we just talked about. These are the rules, like, you know, when you click on MyMathLab for help tools, like the first help they give you is the rule. These are the rules that we just talked about. We just did the power rule, where you drop the exponent down, decrease it by 1, and then you tack on the derivative of the base. That's this rule right here that we just did. Then there's another rule that says the derivative of a constant has to be 0 because a derivative is a rate of change. So if your derivative is constant, so for example here, if I do this, if no matter what I input, my output is constantly going to be 5, that's a constant function, right? So if that's the case, then the derivative has to be 0 because the output never changes, and the derivative is telling me the rate of change from point to point. Plus, if I graphed that line, it would, if the output's always 5, it's a straight line there that would have a slope of 0, right? So the derivative would be 0. If no matter what your input is, if I input a 1 and the output's 5, or I input a 2 and the output's 5, or I input a -3 and the output's 5, if the output's always going to be 5, it makes this a horizontal line, which we know has a slope of 0, so the derivative would be 0 there. So if you just know that, you can save yourself a lot of trouble. You'll know the derivative is 0. And then the sum and difference property, that's just saying if you have multiple terms, you just take the derivative of each term separately. And we did that. So we've already talked about these 3 rules, and I'm going to use them over and over and over again today. Now, the other thing we need to talk about are new ways of writing the notation. Okay, so here we go. This is the one you're used to seeing. Oops. Hold on. My app froze for a second. There it goes. Okay. This is the one we're used to seeing for derivative, right? We're used to seeing this one. Okay. Since f of x is equal to y, right? When you plug in an x, you get a y since they're equivalent. If I take the derivative of f, it's like you're taking the derivative of y. So sometimes they'll say y prime. So if they instead of giving you a function, so instead of saying if f of x equals 5, then the derivative of that function is 0. If they said y is equal to 5, then the derivative of y is 0. It just, if they give it to you in equation format with a y equals, you do y prime. If they give it to you in function format with an f of x equals, you do the f prime. That's all that's saying. But then we have these more interesting ones over here. So let's look at these more interesting ones. Okay, I'm gonna shrink that down. Okay, this notation I'm about to show you is a little bit more intimidating, but we're not going to freak out. Okay, remember how your slope is rise over run. You remember that from algebra? Rise over run. And you rise on the y's, so the y is the change in the y values. The rise is the change in the y values. That's where you did your y2 minus y1. And the run is the change in the x values. That's where you do your x2 minus x1. Remember all that from algebra? Well, they just translate all that into this notation. They say dy over dx. So d stands for delta. Delta is this triangle symbol. In your algebra class, your algebra instructor might have written this: change in y over change in x with a delta symbol. Did anyone see that in algebra? You can give me a thumbs up or agree on your status. Did anyone see that with the delta x, delta y? Okay, a couple people did, a couple people didn't. Oh, it's okay, Trinity. Okay. So yeah, it's all over the place, whether people saw that or not. Okay, if you haven't seen it, it's okay. Did you see at least the rise over run part? The change in y over the change in x? Okay, because then just think about d being like, I don't know, or maybe think about it for derivative. You don't have to think about it for delta, but if you're taking the derivative, you're looking for the change in the y values over the change in the x values. So this is just another way to say the derivative. Instead of f prime, if it's in function notation, or y prime, if it's in equation notation, you can say dy over dx. And then what they will do sometimes is you see that y is your equation. Y is the equation. They'll just pull it out to the side and leave this leftover notation as a fraction. And then sometimes they'll swap that y out for the function notation, but they still leave that other as a fraction. So these all say the exact same thing. All three of these say the exact same thing, and they all say derivative. You're going to see different notation. And this dy over dx notation is going to come in really handy when we do word problems later on. So right now it looks scary, but it's going to help us keep track of units, change in outputs over change in inputs. It'll help us with that marginal analysis we're going to do later. Okay, so this is just different types of notation. So I'm going to start using all of these notations to represent derivatives so you'll get used to seeing them, okay? So let's do some more of these with our power rule. We're going to use power rule. I'm not going to do any limits of the difference quotient today. So here we go. So this first one is written in my first function. It's written in function notation. So they're asking us to find f prime of x, right? But they're matching my function notation. So f prime of x. I'm going to be quiet for a second and let you try this with the power rule, and then we'll see if you get it right. So give it a try. Okay, Marcus thinks it's 10x. Did anyone else get 10x? Emma agrees. Sasha agrees. Okay, cool. Then I can go through this one pretty quickly. Cool. I drop my exponent down. 5 times 2 is 10. I rewrite my base, which is an x. I decrease the exponent by 1, which would be an understood 1 there. But do we have to write an understood 1? Nope. So, and technically, I'm tacking on the derivative of the base. But the derivative of the base is just 1 at this point. Now, just to show you what's going to happen for test 2, you're going to have functions that look like this. Maybe. I don't know if you remember composition of functions from algebra, where you plug a function into a function. But see here in this one, when I input an x, it's not the only thing in the base. There's this linear function there. This one would have to do the chain rule. Here, when I take the derivative of this base, I'm going to end up getting the derivative of this linear function, right? If I have y equals mx plus b here, and I take the derivative, isn't the derivative just going to be a 3? See how it's going to change it up? So right now your base is just going to be a plain x, and so the derivative is going to be a 1. but we're just getting in the habit now so you won't forget to do it later when your base is more complicated than a plain x. So I'm just planting the seed now, but y'all all got that this derivative was 10x. So cool. Okay. What about number 3? Number 3, y equals 6. And since they're using that y equals notation, they're using y prime for the derivative. So, oh, you can't type on the screen when I'm in my app. I was going to have everyone just type their answer. But just looking at this, I know a constant has a derivative of 0. So the derivative should just be 0. But if you're following your power rule, there's an understood x to the 0 there. So you would drop your exponent down, and then I can just stop right there. Doesn't even matter what happens next. If I do 0 times 6, 0, so 0 times 6 is just going to be 0. And even though I get x to the negative 1, if I multiply by 0, it's just going to be 0 on that. Okay, so again, before we do some of the more complicated algebra here, there's 2 more problems. I'm going to be quiet and have you try these on your own, and then I'll quickly go through the answers. So try 4 and 5 on your own. Okay, go ahead and throw your answer to number 4 in the chat. What's the derivative of y with respect to x there on number 4? Yep, -1, right on. And just notice they did a little different notation here. They have a y equals function. They have the y there, but they use that change in y over change in x notation. So when you write it out, you need to do change in y over change in x. So don't write out y prime. You have to use the notation they're asking you for. So change in y over change in x equals, and then if you wanted to write this out, there's an understood 1 in front of that x and an understood 1 exponent. So if you did follow the rule, it'd be 1 times -1 is -1. Rewrite the base, decrease the exponent by 1, tack on the derivative of the base, which is just a plain x, which is just a 1. And then again, when you clean all this up, all that yucky algebra, you would see you just have -1, right? Because x to the 0 is 1, and the derivative of x is 1, and -1 times 1 times 1 is just -1. So you can skip all this if you want. If you know the derivative, just by all means go straight to it. You don't have to do all that. But on number 5 we did, so just to save some time here. Now this one looks a little bit different. So what they've done on this one is they put what y equal to. So instead of telling you that the function was this quadratic equation, or instead of telling you that y was this quadratic equation, they just put it in there with the d of x. So this is the one like these guys, where they pulled the dx out to the front. They pull the dx out to the front, and then this is either the y or the f of x in there. So for this one, when you go to find the derivative, you just do equals. So it's going to look like this when you write it out. You would say, okay, all that derivatives equals, and you go straight to the answer. There's no extra notation to write there. So let's find that derivative real quick. Just using our chain rule on each piece, our power rule. So that would be 2 times -4 is -8. Rewrite the base, decrease the exponent by 1. Technically multiply by the degree of the base, but that's just the derivative of the base. And technically an understood exponent of 1, we don't need to write that. Minus 3x has an understood exponent of 1. I drop the exponent down to the front. 3 times 1 is 3. I rewrite the base. I decrease the exponent by 1, so that's 0. And technically, I tack on the derivative of the base. But x to the 0 power, that's just 1. And the derivative of x, that's just 1. So 3 times 1 times 1, that's just 3. And then our very last thing down here, when we have this 9, that's just a constant. And what's the derivative of a constant? It's 0. So do I have to write it? No, I don't have to write that. It's a constant. So we get this right here. Okay, so give me a thumbs up or a happy face or something if you got 5 right. I'm just trying to see how we feel before we move on. Cool. Isn't that better than the 4-step process, y'all? Can you imagine doing the 4-step process on that one? Oh my gosh, seriously.
Can you explain to me real quick what happens to the 9? I missed that part.
Yeah, no worries. So if I'm actually doing the rule here, let me write out the actual rule for this one. So where it says plus 9, there's no x there. There's no variable component. When I input something into my function, it doesn't affect 9. 9 is a constant. So 9 no matter what. But technically, if you wanted to, there's an x to the 0 there because there's no variable component. So if I did my power rule and I drop the exponent down to the front, I do 9 times 0 is 0. And then rewrite the base and decrease it by 1. But decreasing it by 1, I don't care what this is. If I multiply by 0, the whole derivative of that term is 0. So anytime you have a constant, you know the derivative is going to be 0 because constants don't change and derivatives are rates of change. Did that help? So I was being lazy, y'all. I was being so lazy. I should have worked all this out. And instead of just saying, I know it's 0, I should be reinforcing that power rule. So thank you for asking that, because I'm sure if you were wondering, other people were wondering too. So definitely should add that x to the 0 there. Okay, go ahead.
So would you write that as d over dx equals, or would you do like the little d derivative sign on top?
So on this one, it technically, to match the notation, you would have to do this. You would have to say you'd have to say the derivative of that quadratic function equals what we just got. So like this doesn't have, like, you have to rewrite it all. There's no shortcut for it. Whereas the other, like, I guess technically you could change it to f of x prime, but I think MyMathLab just has you write the answer because technically all of this is a function in here. All of that is a function. So technically when you do all of that, it's the derivative of that function. It's just another way to write the derivative of the stuff inside the parentheses. But I'm trying to think of how, I don't care how you do it on a test, but I think MyMathLab just retypes all of this for you, and then it has that box where you enter the answer, and I think you just put the derivative in. I hope. Yeah, these other ones were a little bit different because, let me zoom out a little bit here. Oh, I'm in the wrong one. On all these other ones, just to emphasize why it's a little different, you were given an equation, f of x equals something, y equals something, y equals something. And here you weren't. See how there's no equal sign anywhere in number 5? There's just this weird notation. Like that's why you just put an answer. Where in all the other ones, you start with an equation. So you had to keep an equation as your answer. And we'll see that more on some other problems here. Go ahead. Arjana?
So, can you hear me?
Yes.
Okay, so we learned how to do it the other way, and now we're learning to do it this way. So when we're tested, can we just do it this way, or will we tested on doing it the other way?
Yeah, I am required to assess limit of the difference quotient. So I'm going to ask one test question, just one, where you have to find the derivative using the limit of the difference quotient. And it'll be a question, probably something like this. Maybe something like, I don't know, 3x squared minus 5 or something. Like, it'll be quadratic. So I'm going to ask you to do it one time with a quadratic function where you have to say, you know, the derivative is the limit of the difference quotient and all that. But after that, please do not ever do it again, because then I have to grade it. So I only want to grade it one time. Yeah, so you'll be required on test 1 to do it once, and then after that, please just do the rule so I don't have to grade it. Isn't that horrible? I'm being so lazy. I don't want to grade that. So yeah, so don't feel like you can forget about the limit of the difference quotient. You can't, but you don't need to use it. And after test 1, you will never use it again. Did I hear a beep for? Oh, got it. Okay, cool. Okay, so let's go ahead and try some more of these, because now we're going to have to use some algebra rules, y'all. Here we go. Okay. Here we go. Algebra time. So, here's a function. So we're given a y equals function, and they're asking you to do the dy over dx. Okay, so it's kind of lining up. We have a really weird exponent, but that's okay. Is 3/2 a constant number? Yeah, it's 1.5, right? It's a constant, it's just ugly. But that's okay, it's gonna follow the same rule. So I'm gonna say dy over dx, because that's the notation they want me to use, equals, and then I follow my rule. I drop the exponent down to the front, so 3/2 times 1. I rewrite the base. I decrease the exponent by 1, so you can just type that in your calculator, but you should end up getting 1/2. And technically we do multiply by the derivative of the base, okay, which is just a 1. So we don't need to write it. And that's your derivative. So even if you see a weird exponent, if it's a constant number, you follow the power rule. But then we get here to number 7. The power rule does not have a square root anywhere in it. So what do you think we need to do? Any ideas? Yeah, x to the 1/2. Very nice. We got to dig deep for our algebra rules here. We're going to rewrite the root as a fractional exponent. So hopefully from algebra you remembered that instead of 6 to the 1/2, there's technically, this is a square root. There's technically an understood root of 2 there. The 6 is just being multiplied to it. We can rewrite that as the radicand to the 1/2 power. And notice I kept my f of x notation there because I have not taken the derivative yet. All I did was rewrite the function, so it stays f of x. And then once you do that, you just follow your rule. Now it's set up for power rule. So then I would say, okay, well, the derivative of that is just 6 times 1/2. So half of 6 is 3. I rewrite my base. I decrease the exponent by 1. So again, just type that in your calculator if you're not comfortable with that. But if I start with 1/2 and I take 1 away, I'm going to get negative 1/2. And then technically we tack on the derivative of the base, which is just a 1. So we don't write it. And that's our answer, and you do not have to do anything to this answer. You can type that directly into MyMathLab. You do not need to be a hero and rewrite it with a root. If you did rewrite it with a root, just so you would know real quick, if I did rewrite it, the negative exponent is only touching the x, so only that x relocates, so the 3 would stay in the numerator, and the x to the 1/2 would relocate to the denominator, and then you would rewrite the fractional exponent as a root. This is being like a rock star. You do not need to do that. You can just stop right here, and MyMathLab will count this right there. Okay, any questions? Oh, go ahead, Michael.
Hey, Professor, when we write or show our work, do you want us to assume the derivative of the base and kind of show that, or do you not mind if we don't do that step at all?
For test 1, you do not have to do that step at all. I'm just planting the seed now because it comes up on test 2 when you actually need to do it, people forget. So I'm like, maybe if I just start on day 1 and you hear me say it that many more times from day 1 on, it'll like sink into our subconscious. But if you don't do it on test 1, it's totally fine. Just know that it's actually happening.
Cool, no worries.
Okay. Any other questions before we try some others here?
How did you get the 3?
So when I dropped my exponent down, that's a good question. Let me erase this real quick. When I dropped my exponent down to the front, so I took my derivative, I dropped the 1/2 down to the front, and there was already a 6 there. So I had to do 1/2 times 6. So you can just do that in your calculator, or you can know that half of 6 is a 3. But when in doubt, type it out. I mean, you're allowed to use a calculator, just use a calculator. Then I rewrote my base, and then I did the exponent minus 1, which came out to be the negative 1/2. That's what you would enter in MyMathLab. Unless you want to be a super amazing rock star, you can enter. It used to be in the old days that you had to match your derivative to the format of the original function, but we don't need to do that anymore because we have amazing technology now that can handle it. Any other questions about number 7 before we move on? Okay, let's look at 8 then. Here we go. Oops. Okay, so for number 8, I have that weird notation again where they just put my, instead of writing f of x equals this function or y of x equals this function, instead of doing that, they put it in this weird notation. So if you want, I would just rewrite that and then put the equal sign and follow your power rule over here, like just so you feel like you're writing enough. So if you want to just rewrite it and say that thing equals what, and then do your power rule, you're good. And even though your exponent is negative, and that's weird, and you're like, I don't know, is -3 a constant number? Yeah, it's -3, right? -3 is -3. So you just follow your power rule. So we drop that exponent to the front. There's already a 5 there, so I need to do 5 times -3. That's a -15. I rewrite my base. I decrease the exponent by 1. If it's at -3 and I decrease it by 1, that's going to drop it down to a -4. And then technically we're multiplying by the derivative of the base, but the derivative of the base is just 1. The derivative of x is 1, so we don't need to write it right now. Okay. So now that we've seen that negative exponents act just like normal exponents because they're constant, let's take a look at number 9. I'm going to let you think on that for a sec. Now, number 9 does not fit my power rule, even though I see an exponent in there, because that base is in the denominator. So it's not fitting my power rule. Remember, my generic power rule had to look like this. There's no fraction in this, but here I have a fraction. So we need to use algebra to rewrite the function. So I'm going to put here, use algebra to rewrite y equals first. So think about what algebra you can do. So I'm going to rewrite it a little bit bigger over here. If I don't want a fraction, that's okay. I can relocate this base into the numerator. And when you change the location of the base, it flips the sign of the exponent. So there's already an understood 1 there in my numerator. And now I'm going to relocate the x to the -8 now. So in algebra, they brainwashed you to always rewrite exponents, negative exponents to be positive. And now I'm telling you, you're going to have to take this nice, pretty positive exponent and rewrite it to be a negative exponent to make it fit the power rule. But once you do that, then you just take the derivative, right? So once I've rewritten that, they're wanting me to use y prime notation. So notice that I have not used y prime yet. All I was doing was rewriting the function. So see how it stayed a y? Y equals. It's the same function. All of those are the same. I just rewrote it. But now that I take the derivative, then I'm going to say y prime and follow my rule. So I drop the exponent down to the front. 1 times negative 8 is going to be negative 8. I rewrite my base. I take the exponent and decrease it by 1. So that's going to be a negative 9. And then technically I tack on the derivative of the base, which is just a 1, which I don't need. Okay. Are there any questions on those before I have you try a couple of your own? Oh, Michael, did you have your hand up? Sorry, I didn't hear the chime.
Previously, sorry. I forgot to put it back down.
Oh yeah, no worries. Okay, so I'm going to be quiet for a minute and I want you to try 10 and 11 and no one put the answers up because I want you to try these and if you get them wrong, maybe you'll know what to ask me. So I'm going to be quiet. Try 10 and 11. Oops. Y'all, I just saw the time, so I want to make sure we get to some other ideas real quick. So let's just quickly go through these together. Here we go. Okay, but it's okay because I'd rather spend time getting a good foundation and we can pick up, make up time later than to like rush this. So here we go. So we see this really weird thing with decimals. I don't know why, but when students see decimals, they freak out. But is 4.5 a constant exponent? Yeah, right? So you just drop it down to the front. So you're going to do 5 times 4.5. So that's going to give you 22.5. You rewrite your base. You decrease the exponent by 1. So that's 3.5. And technically you tack on the derivative of the base. But that's 1. Right? They just use a W instead of an X. But the derivative of a plain variable is just going to be 1. And so we don't need to put that there. So they could use a t for the variable, the derivative of t. The derivative of t would still be 1. The derivative of w would still be 1. The derivative of x would still be 1. If it's a plain variable, no matter what variable they use, if it's a plain variable, the derivative is going to be a 1. Okay. So don't get too used to seeing x's here. And then, I need to finish it because we're subtracting 4.5 w to the first. That's the understood. I drop the exponent down. 4.5 times 1 is 4.5. I rewrite the base. I decrease the exponent by 1, which is technically a 0. And then I tack on the derivative of the base. Well, the derivative of a plain variable is just 1, so I don't need to write that. W to the 0 power, any non-zero base to the 0 power is just 1. 4.5 times 1 times 1 is just 4.5. So hopefully you got 22.5 w to the 3.5 minus 4.5, nothing else written there because it's technically times 1, which we don't need. Okay, so show me a quick status or raise your hand if you have a question on number 10. Okay, got some happy faces. Michael's happy. Patrick's happy. Lots of happy faces. Okay. And this next one has a lot of algebra going on here. So let's take a look at this one. We'll slow down a little bit for this one because I want to make sure, usually y'all in a calculus class, it's the algebra that gets students. It's not the calculus. It's almost always the algebra. So here we go. I'm going to rewrite the function. I need to rewrite y. Okay. So let's take a look at this first term here, this first one. Here's my base. It has a constant exponent. It's in the numerator. All of that is fine. If it helps, you can rewrite it like this. You can pull the 5/4 out to the front like a slope. You know how we pull the the slope out to the front, I can make like the coefficient in front a fraction, and then I have the base and the exponent there. If it helps you see the power rule a little bit better, you can rewrite it. Again, no calculus has happened. I just rewrote my term there. But the next one, I have that base in the denominator. Oops. The exponent 3 is only immediately touching the x. It's not touching the 5. So when I go to relocate that, I'm only relocating the x cubed to the top. So it would look like this. There's already a 2 up there. When the x cubed relocates, it becomes x to the negative 3, and the 5 stays on bottom. So again, if you want to pull this fraction out to the front, you would have 5/4 x to the third minus 2/5 x to the negative 3. And all of that is just rewriting the original equation. We have not done any calculus yet. But let me pause there to see if there's any questions on how I rewrote my equation with algebra. How are you feeling on that? Give me a status or a thumbs up. How are you feeling with just the algebra that happened? Okay, now you can do the calculus. So then the calculus says, drop the exponent down to the front. As awful as it is, you're going to do 5/4 times 3. And just heads up, I think my MATLAB makes you put that as a fraction. Keep it as a fraction. I don't think it lets you put a decimal. I could be wrong. Luckily, it's a pretty decimal. So if you wanted to put it as 3.75, you could. I think my MATLAB makes you keep it as 15/4, but just use your calculator. When in doubt, just if you need help with your calculator, come to office hours and I can help you with fractions on your calculator. And then I rewrite the base and I decrease that exponent by 1. So it becomes a squared. Technically times the derivative of x, which is just 1, so I don't write. And then on the other one, same thing's going to happen here. I drop this down, but be careful. When I drop it down, there's already a subtracting fraction. So you have a subtraction there. You have a negative coming down. So when you multiply those together, you're going to get that double negative, which is going to make it a plus. And then again, you know, I think my MATLAB wants you to write 6/5, but since it's a pretty decimal, I think you could get away with writing 1.2. But just to be safe, I'm going to write 6/5 x to the, I decrease the exponent by 1, that's going to be x to the negative 4th, technically times the derivative of the base, which we don't need. Okay, I know that one was nasty because not only were there fractions, but you had to rewrite it with algebra. Yucky, yucky. If you did not get that one correct, come see me in office hours if you need help with your calculator. I'll pause for a second to see if there's any questions. Okay, then this is what we're going to do. I am going to skip number 12. I'll write it up in the answer key. Oh, actually, no, we need to do number 12. Luckily, it goes super duper fast because we need to do number 12C because this is an algebra idea that I want to make sure we review that algebra. But the calculus part is easy, right? Because look at this function they gave us on number 12. They gave us this nice polynomial function and they want you to find the derivative, which you could do blindfolded now, I'm sure, right? So I'm going to find the derivative real quick just using my power rule. So I drop my 4 down to the front. I rewrite the base. I decrease the exponent. Okay. Minus. I drop my exponent down to the front. 8 times 2 is going to be 16. I rewrite the base. I decrease the exponent. Okay, so we get this derivative here. I'm kind of speeding through that part. And then I was going to have you just plug some numbers into the derivative like we did last time, but I'm going to skip that real quick. But if we did that, at -1, you should get a positive slope. And at +1, you should get a negative slope. I was going to talk about that, but we can fast forward through that. Because I want to get down here to C, because C has some algebra. C says, find the values of x where the tangent line is horizontal, where the slope is 0. So let's look at this graph, and without doing algebra, let's just look at it graphically. Where do you think the slope of the tangent line would be 0? So here's the slope of my tangent line. It's negative. I have a negative slope, negative slope. Then at this point, see how it goes horizontal? My slope would be 0 there. And then it goes positive, positive, positive. And then here, my slope hits 0 again. And then negative, negative, my slope hits 0 again. And so on. So the slope hits 0 at these peaks and valleys, at the local mins and the local maxes. So just throw me a smiley face or thumbs up. Did y'all talk about local mins and local maxes in your algebra class? Okay, so from the people, okay, so local mins and local maxes. Those are going to be really important to us in calculus, because if I want to find the minimum cost, I'll just know, oh, the derivative is 0 there, right? Or if I want to find the maximum profit, I'll know, oh, the derivative is 0 there. So knowing where the derivative is 0 is super, super, super duper helpful. The problem is we won't always have a graph. So if they want you to find the values of x where the tangent line is horizontal, this is what you have to know. You have to know the tangent line is going to translate to the derivative. The derivative describes the tangent line. And you have to know that it's horizontal when the derivative is equal to 0. So basically, you have to be able to translate that where you take this derivative that you just found, that derivative rule that you just found algebraically with your power rule, and set it equal to 0 and ask yourself what values of x would make that happen. So this is all algebra based. We know what they are from looking at the graph. We know it should happen at x equals -2 because the tangent line was 0, at x equals 0 because the tangent line was 0, and again at +2. We can see them on the graph. How would we get that algebraically? Well, you just have to use your zero product principle. So think back to algebra. I need to factor this. So always ask yourself, is there a GCF you can factor out from the very beginning? And the answer is yes. This has a GCF of 4x, so we're going to factor out the 4x. That would leave me an x squared minus 4. And then there's all kinds of algebra you can do, but I recognize that I have a difference of squares, so I'm going to go ahead and factor that a little further. And I know I'm kind of fast forwarding through this algebra because it's supposed to be prerequisite. If this is really rusty for you, come see me. But then we have 3 things multiplying. We have a monomial times a binomial times a binomial. They're all multiplying to 0. So either 4 times x equals 0, or x minus 2 is equal to 0, or x plus 2 is equal to 0. And then you solve those individually. The only way 4 times x can be 0 is if x is 0, right? The only way I can get 0 is if I multiply by 0, so x has to be a 0. And the only way x minus 2 can be 0 is if x is a +2, because 2 minus 2 would give me 0. And the only way x plus 2 could be 0 is if x is a -2, because -2 plus 2 would be 0. So you can get those 3 really important points, those x values that create those local mins and local maxes, just by setting the derivative equal to 0. I don't know, how are you feeling on that?